Well, hello everybody. I am making this video on a very cold day. I see some sleet on the ground outside, and in my office it's 63 degrees. I don't have a heater or air conditioner in my office, but someday I'll get that sorted out. For now it's going to be very cold. Anyway, so this video I wanted to be kind of like a quick summary video and have some examples in it. Alright, so if you watch this, you get a brief overview, you'd see some examples, and then maybe that would be all you need to try to work the assignment. So in the video there will be two principles for solving equations that have logarithms. Okay, so in other words, you see an equation like this and it's got a logarithm in it, and the objective is to solve it, like one of these. Okay, so you see these equations, they've got logarithms. You need some kind of principle to follow, some kind of rule to follow, and that's what I'll start with. Okay, so first principle applies to this situation where you can isolate one logarithm on one side of the equation, like this. Okay, and if you get in that scenario, maybe you start there, or maybe it takes a few steps to get to that point, then what you do is this. Okay, you raise this number to this power and you say it's equal to whatever that is, and then you can solve from that point. So okay, so like wherever you start, you get here and then you apply this pattern, okay, and then you get that, and then you solve it from that point. Okay, so this is kind of like right in here, this is like the middle of the problem. Alright, but once you see a few examples of how I get to this point and apply this pattern and solve it, and you'll see how the whole pattern is applied. Okay, so let's not worry about this other principle until we get to an example that looks like that. I want to just show you some examples of this so you can see what I mean right away. But I want to say before I show you any examples that no matter which principle you apply, if you're solving an equation that starts off with a logarithm in it, like this one, I'm looking at it, there's a logarithm in it from the very beginning, then we should check our answers. Okay, check our answers to rule out that we're not ending up with a logarithm of a negative number or a logarithm of 0, because each of those are impossible calculations, and so we can't really say we have an answer if it leads to one of these happening. And that kind of thing can come up when you're solving an equation with a logarithm. Alright, so let's try this one first. It says solve the equation log base 2 of 5x minus 1 is equal to 4. Now, I think this is a pretty clear instance of having that, where we have isolated one logarithm on one side of the equation. Okay, so what I had mentioned in that first principle was the pattern that you should apply if you're in that situation is to say that this number raised to that power will give you what's in here, and then you solve it from that point. So I will do that then. Okay, so we'll get 5x minus 1 is equal to 2 to the 4th power. Now that doesn't give us the answer right away. Remember I said that we would get in this situation and we would apply a pattern and get there, but we'd have to solve it from that point. Alright, so alright, let's see, let's see, how could we solve this? Like, you know, I can't say that you'll end up in the same situation every time you apply this pattern, but like on a case-by-case basis, we've got to think about what we're going to do. So what I would say is, well, I know what 2 to the 4th power is, so I might as well incorporate that into my work. So that's 16. Okay, and then I see that always what I want to know is, I want to know what the variable is. I want to know what the x is. So I want to isolate this x. I could add 1 to both sides and get like that. And then again, because I want to solve for the x, I could divide both sides by 5 and I get 17 over 5. Okay, and then that appears to be my answer. Okay, let's see how that pattern is applied. See how that first principle is applied. Now, so I get 17 over 5, and I think that that will work for us, but I did say that no matter which one of these principles you're using, anytime we're solving an equation that starts with a logarithm in it, we should check our answer to rule out that we're not getting a logarithm of a negative or 0. So, okay, I need to make sure that this number doesn't cause that in there to be 0 or negative. So I'm going to go ahead and check it because that's what I recommend you to do. Okay, what does it mean though for it's a number to be a solution to an equation? It means if I take that number and I put it into the equation, it will work. All right, so I'm going to do that, and I'm going to make sure that it works. So I'll get log base 2, 5 times 17 over 5, okay, minus 1 is equal to 4. And I'll put a question mark just to be dramatic about it, like to say I'm wondering if this works. So let's see, 5 times 17 over 5, that's 17. Okay, and 17 minus 1 is 16. So now I get here. Now, I could say that I'm okay at this point, because when you check your answer for one of these cases, or a logarithmic equation, I'm trying to check it to make sure that I'm not getting a negative inside the logarithm or 0. Some impossible calculation. But I'm not getting that. I got 16, so that's okay. But if you want to take it down to the very end and make sure that, yes, all the numbers agree, then go ahead and do that, all right? So is it true that log base 2 of 16 is 4? Is that true? That is true. Log base 2 of 16 is 4. And why is that? Because if you take 2 to the 4th power, you will get 16. Okay, so it does work. All right, so let's see. Let's do another one. Now, this one has kind of a similar appearance to the first one, but it's different enough to be a separate example. Now, why would I think that this first pattern might apply? It says isolate one logarithm on one side. Do you think you could do that? Like this one, obviously there was one logarithm on one side of the equation. That's the way that it looked. I mean, it was almost exactly like this first principle is. It's log base, you know, whatever of whatever equals some other number. Okay, this one, well, let me see, how many logarithms over here? Log base 5x plus 8 plus log base, so there's 2 of them. So it's not exactly like this one, okay? But do you think you could get it to where you could isolate one logarithm on one side? In other words, can we turn these 2 logarithms into one logarithm? Is there some way to do that? There is some way to do that. There's this rule. Logarithms have lots of rules, but it says if you have logarithm of some base b of m plus logarithm of a matching base b of some other number n, then you can combine those like this. Log base b of the number m times n. All right, so you might say it like this: with logarithms, addition on the outside makes for multiplication on the inside. So I could do that. Then I could turn these 2 logarithms into one logarithm. And then if we did that, what would we have? I mean, I guess part of doing math is being able to see ahead a little bit and know where you're going and to know that you're going in the right direction. Yeah, I mean, if I could turn these 2 logarithms into one, like put them together, then it would be like this one, and we just solved that one. Maybe it wouldn't be that much different, okay? So what I would get is I would get like this. I would say log base 5, and then I'd have to say, well, I got to take this thing, which is x plus 8, times this thing, which is x plus 4, okay, equals to 1. Now, it is like this one, isn't it? Yeah, I mean, it's like logarithm, got a base, got something in there, got a number over here. Okay, so then what did we say that we would do if you're ever in this situation where you can isolate one logarithm on one side? Well, you take this number, you raise that power, and you say you get whatever is in here. So that's what you should do. That's what's applicable at this point. So we'll go ahead and say, well, that's what we're doing. We're going to take like this and say we get that. And if that happens, we'll get x plus 8 times x plus 4. And we'll have to say that's equal to 5 to the first power, won't we? Okay. Now, when I had written my principles up here for you, I said that once you were in this scenario and you applied this pattern, that you would have to solve it from that point. And how you do that might vary from one problem to the next. Okay? So here, like, well, how do I solve this one? I'd have to know. Now, when you're in math class, like typically at our school, then it's not like on the assignment or the homework you'll see something that is totally different, totally unlike anything you've seen before. Okay, so I'll show you how to do this, and then I'm saying that, well, you'll probably see something similar to this at some point. It's not like you'd have to come up with this all by yourself out of nowhere. Okay, so here's what you do. We want to multiply all this out and then ultimately solve it by factoring. Okay, that's what we'll do when we're in this situation. So for me to multiply all that out, I'll use FOIL multiplication to multiply all that out. I'll get x squared plus 12x plus 32, and over here 5 to the first power, 5. Now ultimately I'm going to solve this by factoring, and to do that I need a 0 on one side and I need to factor the other side. So I'm going to get a 0 over here, and that will give me like this. I get 32, take away 5, that'll be 27, and I get 0. Alright, and now I factor, and the way you factor this one is like that. Okay, and then each factor gives you an answer. This first factor is one possible answer, and the second factor is another. Now, within this process, there's all kinds of things that we could talk about. All right, that's one thing about teaching math that's difficult. Is, you know, we have our class and everybody's supposed to be to a certain point, and that point is that you've seen all this before, like that you know how to do FOIL multiplication, okay, and that you know that this type of equation can be solved by factoring, and that the rationale behind that is that if this thing times this thing is 0, then one of those things must be 0, because to multiply and get 0, the only way to do that is to multiply by 0. So there's lots of little things that you'll need to know along the way. Now, in practice, that might not be the case. It might not be the case that you remember every little bit of this all the way through. So if something does come up where you see it as an aspect of one of the problems, but you just don't remember it, then that's something we should talk about. Okay. So anyway, I get all the way down there, and I get -3 and -9. So it looks like I get 2 answers. But let's see. There is this catch with logarithmic equations that we need to check those answers to rule out that we're not getting a negative inside the logarithm or 0. So, okay. Let's see. Let's check over here. And I think one of these is going to be okay and the other isn't. So the -3 is going to be okay. So take that and starting equation, the one at the beginning, this is the one we're trying to solve, and we'll put -3 in. Okay? We'll see if it works. Now -3 is a negative number, but that doesn't mean that when you put it into the equation that it causes the number in the logarithm to be negative, because look, I'm trying to solve this equation up here. If I put -3 in it, what do I get? What's -3 plus 8? That would be 5. Okay, so I'll get log base 5 of 5. Okay, and then say I put -3 right here. So -3 plus 4, that would be 1. Log base 5 of 1 equals 1, question mark. Now, so it looks like I'm okay, because what I'm trying to rule out when I check my answers in this kind of equation is that I'm not getting a negative or 0. Okay, and so this one, it's all right then. Okay, I got 5, I got 1. Both of these can be calculated. I've made other videos regarding how you calculate any individual logarithm, but log base 5 of 5 is 1 because 5 to the first power is 5, and log base 5 of 1 is 0 because 5 to the 0 power is 1. And so this equation reduces to the statement that 1 plus 0 is 1, and that's something everybody would agree with. Okay, so negative 3 works. What about negative 9? Well, here's where I see a problem. Look what happens when you put negative 9 in. What's negative 9 plus 8? That's negative 1. Okay, so already we have a problem because I can't calculate what log base 5 of negative 1 is. It's an impossible calculation. So this number, like right off the bat, I put it in right away, I get something that is not possible to calculate, so this can't be an answer. So, but nonetheless, let me fill the whole thing out. We'll get negative 9 plus 4, that's negative 5. Log base 5 negative 5 equals 1. Oops. And then that's like no good right from the beginning. I can't take it any further. Okay, and it ultimately does not produce a true statement. A solution would produce a true statement once you put the number in, like 1 plus 0 is 1 is true. Here we can't even calculate. All right, so let's give our final answer like this. So in the box I'll put the final answer. There it is. Negative 9 is not one of the answers. It's just negative 3. Okay, so let's look at maybe like 3 more. Now take a look at this one and kind of think about the progression that I'm trying to show you. I showed you this one where it's fairly direct to this principle, like right away. Okay. Then I showed you one where, well, we had to do like a step to get to that point, and then we had to do several other things after that, but we still use this first principle that I have up here. All right. And now, like, how does this fit in? Okay. Can I use that same principle that I showed you for those first 2 problems? All right. Well, here I have 2 logarithms in a number. So it's like kind of like this one. There's 2 logarithms in a number. And it's kind of like this one where we have logarithms on one side, number on the other side. I guess it would just come down to, can you combine these 2 logarithms into one? Okay. Is it possible? It says log, oh, there's no base there. What does that mean? It means the base is 10. So remember, if I have logarithm written like that of some number, no base is indicated, then it's assumed there that the base is 10. So, all right, the base is 10 there. But I've got log base 10 of x minus log base 10 of x plus 10 is negative 1. Could I combine these in the same way that I could combine those? Because if I could, then I could work it probably more or less like this one. So yeah, there's a rule for that. There's lots of rules for logarithms. So if I get log base b of some number m minus log base b of some number n, those can be combined to log base b of the number m divided by the number n. So with logarithms, you could say subtraction on the outside amounts to division on the inside. So that would give me a way to combine both of these into one. Why would I want to do that? Well, because my principle is that we can isolate one logarithm on one side of the equation. All right, so let's see. That would make this log base 10 of x over x plus 10, wouldn't it? Yeah, I mean, this number divided by that one. Subtraction and division. Okay, so now we're in a situation like this. One logarithm isolated on one side of the equation, or like this. So like we know what to do. We know that there's a pattern that we apply. I'm going to write that there's a base there and it's 10, and then I'll show you that what we do is we take 10 and we raise it to that power and we say that we get whatever's in there, right? Okay, so if you do that, I'll get x over x plus 10 is 10 to the minus 1 power. Okay, now from there, let's do this. Here's the way I'll solve it. There's always, almost always, room for variability in math. You can solve the same problem in maybe several slightly different ways. I'm going to say that 10 to the minus 1 power is 1 over 10 to the first power, because that's how negative exponents are understood. So that's 1 over 10. The reason I'll do it that way is because then I can apply this principle of cross multiplication. So there's lots of rules that apply to logarithms. There's lots of rules in math, period. Okay. Cross multiplying looks like this. So say you have a fraction on one side of an equation. It says a over b, whatever the fraction is. And you have it equal to a fraction on the other side of the equation, c over d. If you're ever in that scenario, then we can multiply crossways and get this. A times d is equal to b times c. And then you could solve it from there. So, but you have to be in this exact scenario. A fraction, a over b, equals some other fraction, c over d. Then you cross multiply, no more fractions. Okay? So, in my case, if I were to apply this pattern, this cross multiplying, to this, I would get x times 10, or otherwise known as 10x, and x plus 10 times 1, otherwise known as x plus 10. Okay? Then, I'm almost there. I want to solve for the x. I'll subtract x from both sides, and I'll get like this. And then I'll divide both sides by 9, and I'll get 10 divided by 9. Okay. And then that's my answer. Alright. Now, 10 divided by 9 will work. You can take it and plug it in both of these, and you won't get a negative in there. And we said before, that's what we're trying to rule out. At the same time, if you want to take that number and plug it into the equation and work it all the way out to show that it's true, then do that, all right? But at least can we verify that this number, if plugged in there and there, it's not going to give me a negative, it's not going to give me 0. And I'm going to take it then that it's okay, and it is. All right. Okay. Let's do one more then, like this, but where the numbers get a little strange. Okay. So here I have one that looks a lot like that. You know, I mean, it's like this is a logarithm, then I got subtraction, and then I've got another logarithm, and then I got a number. Okay. But it says ln instead of log. So ln is a logarithm. It's called the natural logarithm. Okay. And it is a logarithm of base number e. All right. E is a number that's about equal to 2.718. It's used for the calculation of radioactive decay, population models, compound interest, all kinds of things. All right. But for now, I'm telling you that it is a number. It's not a nice round number like 10, but it's still a number. And when you see ln, that's called the natural logarithm. It's a logarithm of base number e, where e is about 2.718. Okay, that's what we're dealing with here. But otherwise, it's still just like this other one. Why don't we try to solve it the same way? So let's see. What was the rule for combining two logarithms into one if they're subtracted? So we said subtraction on the outside amounts to division on the inside. So let's see then. If I did that, I would get ln x plus 10 divided by x. That's how I would combine these two. That's how the subtraction between them would combine them into one logarithm. Subtraction on the outside, division on the inside, like that. And then I get like that. Okay? From there, I should apply this pattern. Okay? Where did we begin? We said here's our first principle. If you should end up in this scenario where you can isolate one logarithm on one side of the equation, take the base number, raise it to this power, and say it's equal to this, and then solve it from that point. So I should do that, but maybe I make it a little bit more clear. And instead of writing Ln, I'll write LOG and put the base intentionally as E, E being 2.718. But I'll leave it as just E, that's the number. Okay, all right, so then we said, well, you got to take that and you raise it to this power, and then you say you get this. So let's see what would it look like if that was applied. I'll get x plus 10 over x is equal to E squared. Okay, all right. Now, I remember I just told you about this principle of cross multiplication. If we ever have an equation where one fraction is equal to another, a over b equals c over d, that's when we can cross multiply and then eliminate all fractions. Okay, all right, so that's when cross multiplication can be applied and how to apply it. Okay, so I've got that over here. Maybe I'll make it a little bit more bold by putting this with a 1 like that. All right, so let's cross multiply. I'll get x plus 10 times 1. And then I'll get x times e squared. Now, e squared is its own number. Okay? I could take my calculator and figure out what e squared is, but we should avoid rounding numbers as we're trying to work things out, because every time you round a number, you get round off error, and when that happens, the error gets magnified as you continue to work with your numbers. So I'm gonna wait till the end. Now, the instructions I'm giving say round the answer to 4 decimal places. By that I mean the final answer. Okay, so let's do this. Let me give a little analogy here. This is kind of like solving this. Okay, say I had the equation x plus 10 is equal to 5x. All right, how would I solve that? I need to combine the x's together. So I would subtract 5x from both sides, and I would also move the 10 to the other side. Okay, I'm going to solve this one in the same way. The numbers don't look nearly as agreeable, but I'm going to do the same thing as over here. So could you agree with me that if I have x plus 10 equals 5x, and I want to solve that equation, subtracting 5x from both sides, moving the 10 over to the other side. How do you combine, though, x minus 5x? Those are like terms. And you combine like terms by combining the coefficients. 1 minus 5x. You see? You get negative 4x is equal to 10. And then you divide both sides, you get 10 over negative 4. Okay. So I will have to do that same thing here. It's just I wanted to give you this analogy because e squared is not nearly as friendly of a number as 5, but it is just a number still, and so we treat it like a number. We do all the same things with it. We can treat it like we treat the 5 here. Okay, so I'm going to get x minus e squared x, putting this over there with that x to combine the terms with the x, and then I'll move the 10 over here like that. And then I said, well, these would be like terms. This is like 1x minus 5x. 1x minus e squared x. How do you combine like terms? We combine the coefficients. So 1 minus e squared times x is negative 10. All right. So now I'm like at this point, what do you think I'd do from there to solve it all the way? Divide by this number, 1 minus e squared. I mean, 1 minus e squared, I would need a calculator to tell you what that is. I could roughly tell you what it is, you know, off the top of my head, but to really know, I would need a calculator. It's not quite like 1 minus 5. 1 minus 5 is just negative 4. It's a nice round number. Here, this is not a nice round number. I'm going to leave it. I'll round my final answer, though. So let's take this over here. And if I were to divide both sides by 1 minus e squared, then it would look like that, and it would isolate the x, and it would give me an answer. This is called the exact answer. Sometimes on your assignment, you may be asked to give the exact answer. By that, that means no rounding. Why is it called exact then? Well, because whenever you round a number, there's something called rounding error that's in it. It's not exact. It's not perfect anymore. So if you were working anything, And it said to give the exact answer. That means just whatever the numbers are not rounded. So here they are. That's the exact answer. My instructions that I gave for the sake of this example were to round the answer to 4 decimal places. So let's see it. Negative 10 divide by 1 minus e squared. And your calculator will have this ability, if it's a scientific calculator, to do calculations with the number e. Alright, if you're not sure how that's done, and that's something that you should ask about. Anyway, so I get this. I get 1.5652. So make sure that you could do that calculation with your calculator. Alright, can't really give general advice because everybody's calculator is different, but you'll have a key or a function somewhere that allows you to calculate with e. Alright, okay, so there it is, rounded to 4 decimal places. That's my final answer. All right, now there was one more thing, wasn't it? We should check our answers in either case to rule out that our answer, so to speak, doesn't produce a negative or 0 inside the logarithm. All right, so let's see. What if you took 1.5652, or 1.5 basically, and you put it in there, x plus 10, would that make a negative? No. 1.5, say you put it here, would that make a negative or 0? No. It's okay. It checks out. All right? If you want to plug it in and check it all the way to the very end, then you can do that. But at the bare minimum, you need to check to rule out that you don't have a negative or 0 in the logarithm. And in this case, we don't, and everything is okay. All right. Let's do one more, because in the video I said there were 2 principles that we talked about, and so far I've done 4 examples with this first principle. The other principle is different in this regard. So principle 1, if we can isolate one logarithm on one side, you see, like this. Those are the 4 examples I just showed you. As opposed to the second principle, where there's one logarithm on each side. So it's like, and the bases match. So it's like on one side it says log base b of some number m. On the other side, it's log base b of some other number n. Now, if you're ever in that situation, and you might have to do a little work to get here, but say you find yourself here, you get here, intentionally or not, then you can say that this number must be the same as this one. M is equal to n, and then you solve it from that point. You know, maybe it's easy to see why you could do that. If everything else matches in the equation, then these numbers in there must also match. You know, if each side looks the same except for the middle part, and the middle parts must be equal. It's kind of like if I said 2 to the x power is equal to 2 to the 5th power. What does the x have to be in order for this equation to be true? Well, the 2's already match, so the x has to match the 5. It's kind of like that, all right? So hopefully this one isn't too far out there. But I think that that's the one that we should apply to this, because I already have a logarithm on one side, and I've got 2 logarithms on the other. If I could take that and reduce it to 1 logarithm on each side with matching bases, then it's like I just have to say the insides are equal, and then I solve it from that point. So think about it. Could you get there? There's 1 logarithm here, and there's 2 over there. Could you combine these 2 into 1? Because if you could, then you would be in this scenario and you could solve it in that way. Well, yes, you can combine those with logarithms. Addition on the outside is multiplication on the inside. It gives you a way to combine them together. So yes, I could do that. Like, I will leave this one alone. Okay. And I want to combine these 2 into 1. And that would be that y minus 5 times 2 is what goes in there. I'm going to write it like this, though. Okay, right? That's how you do it. That's how you can combine these. There's 2 of them, combine them into 1. Addition on the outside makes multiplication on the inside. Now, what did that principle say to do? We can say that these insides are equal. Everything else matches, so those inside parts have to match too. So think about it. I mean, I got log base 3, log base 3. It just must be that this thing right here has to be the same as that thing over there. They have to match. How else could these two things on either side be equal to each other, as the equation says? All right, so I get y plus 3 equals 2 times y minus 5. I'll have to solve it from this point, but in this case, that shouldn't be that hard to do. I will multiply through there. I'll get 2y minus 10, okay. And then I'll combine the y's on one side and numbers on the other side. That's how I'd solve this particular equation. So like if I took 2y and subtracted it from both sides, it'd be negative y. If I subtracted 3, I'd get negative 13, like that. Negative 10, take away 3. And then to solve all the way for y, if I multiplied both sides by negative 1, or if I divided both sides by negative 1, either way, I get that y is equal to 13. Does 13 cause a negative anywhere up here where it shouldn't? No, so 13 is okay. 13 is the answer. All right, there you go. Now, so that's our two principles. Now I have to show you all this, right? But then there's a caveat to all of it, that if, as we went through this, you weren't sure about any of the intermediate steps beyond the principles, because it might be the case when I just show you the principle and then I show you the step where I apply it, is no big deal because you're seeing it right now. But there's lots of other things that you've got to know about beyond that, okay? So that's when we need to talk further about factoring, multiplying, how you solve different kinds of equations that look different. I've reviewed lots of other things, cross-multiplying, adding like terms that have weird numbers like e squared in it. There's all kinds of other things that we could talk about beyond that. And if that's necessary, you'll just have to let me know.